Hello everybody, in this video I am going to talk about simultaneity and clock synchronization in special relativity. Right. What is simultaneity? Two events that are separated by some distance are said to be simultaneous if they occur at the same time. This is the idea of simultaneity that we have from the Galilean and Newtonian school of thoughts. Right, that is because time was considered to be universal and time flows uniformly for all inertial observers in Newtonian mechanics, and therefore this idea of simultaneity existed for several hundred years. But relativity changed all of this, right? Even if you look at the Lorentz Transformation equations, which we have discussed in a separate video, you could clearly see that the transformation equation T prime is equal to T minus, right, ux over c squared divided by 1 minus u squared over c squared. This equation clearly tells that the time measured by an observer O prime in a frame of reference, which is in relative motion with a velocity u with respect to an observer O, who measures the time of the same event to be t. So there is a difference in time measured by the two observers. So the very idea of simultaneity can be traced, the origin of the idea of simultaneity in relativity can be traced back to even Lorentz transformation equations, right? Therefore, in relativity, two events that are separated by some distance and occur at the same time, that is simultaneously in one frame of reference, need not be simultaneous in another frame of reference. So if you think about this, this is a very dramatic idea, right? It is very much against our expected notions of simultaneity, right? So two events that are simultaneous in one frame of reference need not be simultaneous in another frame of reference, provided the two events are separated by some distance. Now let us discuss this with an example, right? So let us say that two controlled explosions are triggered in two different cities. Let us say New York and Chicago. Two controlled explosions are triggered and they are separated by some distance, and both occur at the same time for observers on Earth. So let us call them observer O, an observer on Earth. The time of these two events, let us say, are the same. So for the Earth-based observer, therefore, these two events occur at the same time. So T1 must be equal to T2. If you consider another observer who is in relative motion at a velocity v with respect to this, let us say on a spaceship, let us call him observer O prime. He is traveling with respect to the Earth at a velocity u. If he tries to measure the explosions, he would think that these two explosions did not occur simultaneously, right? So according to this observer O prime, these two events occurred at slightly different times. Because his direction of motion is in this direction, he would understand that this event occurred first and then this event occurred. Therefore, for him, T1 is not equal to T2. So these two events are not, and of course in his frame of reference the times are also going to be different. So I would say T1 prime is not equal to T2 prime. This is the idea of simultaneity in relativity, right? What it has got to do with clock synchronization. So on Earth, if you try to synchronize two clocks, for normal purposes, we would just look at these two clocks, keep them close by and try to adjust the time. But for scientific experiments, the time synchronization is a major issue. So we need nanosecond accuracy for clocks for some of the experiments in science and technology. So for those experiments, the time of travel of the signal from one clock to the other clock while two clocks are being synchronized is also very important. How much time it takes for the signal from one clock to travel to the other clock. Therefore, accordingly, the clocks have to be adjusted, taking into account these corrections as well, right? And therefore, clock synchronization is a very important issue. Let us discuss now in some detail how the synchronization of clocks is getting affected because of relativistic principles. Okay, let us try to understand the clock synchronization using a thought experiment. In this experiment, we have a light source. Let us say it is a flashing light source, and there are two clocks, C1 and C2, separated by a distance d. Right? These clocks and this entire setup is in the frame of reference of, let us say, observer O on Earth. Now, these two clocks have to be synchronized based on the signal received from this light source by these two clocks. Now, light travels at a velocity c and it travels a distance d by 2 on either side. So, the two clocks have to receive the light signal simultaneously for this frame of reference. So, therefore, the light travels the distance between these two clocks. Now, these are two events. Please remember that these are two events, event 1 and event 2. Right? And these two events are separated by a distance d on Earth. What is event 1? The clock C1 receiving the light signal. What is event 2? The clock C2 receiving the same light signal. Right? And then what is the coordinate for the event 1? The coordinate for the event 1 in this particular frame of reference, let us call that as x1. At what time it is occurring? t1. Similarly, the coordinate of the second event is occurring at a point x2 at a time t2. Now, this is all for the observer O who is fixated on the Earth. Now, suppose there is an observer moving. Let us call him observer O prime in another frame of reference at a velocity, let us say u, with respect to this frame of reference. Now, for the same two events, he would measure a different set of coordinates for the position of the events as well as the time coordinates for the same events. So, let us call those positions and time coordinates as x1 prime, t1 prime for the first event, and x2 prime, t2 prime for the second event. Now, for the Earth observer, we know that t1 is equal to t2. Why? Because we know that the distance traveled by the light flash is going to be d by 2 on both sides. So, it is going to take same time for the light from this particular source, which is equidistant from the two clocks, to reach the two clocks. Right? So, t1 is equal to, if the speed of light is c, t1 is equal to d by 2c, and t2 also must be therefore equal to d by 2c. Now, we know the Lorentz transformation equations for transformation of time coordinate from one frame of reference to another frame of reference. Let us write it down. t1 prime is equal to, we know that it is t minus, right, ux by c squared, square root of 1 minus u squared over c squared. This is the expression for the Lorentz transformation of time coordinates between two frames of reference. So, if you use this one now, we would write t1 prime is equal to t1 in this case minus ux1 over c squared, the entire thing over 1 minus u squared over c squared. Now, if you substitute these values, that is going to be t1 is d by 2c minus u times x1 is 0, because this is the origin of the coordinate system. We can fix it here, and we can say that x2 is at d because the distance is d. For the Earth-based observer, we can fix the origin here. So, that way the second term would go off. So we can straight away say that this is going to be d over 2c square root of 1 minus u squared over c squared. That is for the t1 prime. What about the t2 prime for him? If you write t2 prime for the primed observer, that would be t2 minus ux2 over c squared, the entire thing over 1 minus u squared over c squared. Therefore, I can write t2 is again d over 2c minus u into x2 is d. So, u d over c squared divided by square root of 1 minus u squared over c squared. Now, these two time coordinates are the times for the events, same two events for the observer who is in motion with respect to observer O. And we can clearly see that this term is there present as the first term, and then there is an additional term. So, if we take a difference between these two frames, between these two time coordinates, we would see that the difference is nothing but del t prime. The difference del t prime is equal to t1 prime minus t2 prime, which would be equal to the first terms in both t1 prime and t2 prime are identical, so they would cancel out, and then this term alone would remain, that is ud over c squared over square root of 1 minus u squared over c squared. Now, this term shows us the lack of synchronization between these two clocks for an observer O prime who is traveling relative to the observer O with a velocity u. Right? That is what this term tells us. So, we can clearly see that because of the lack of simultaneity between these two inertial observers in two different frames of reference, there is also a lack of synchronization between the clocks, same two clocks carried by an observer O prime. That is what one can conclude based on this result. So, the first term in our expression for Lorentz transformation, time expression for Lorentz transformation, this gives us time dilation, whereas the second term gives us the lack of synchronization of clocks. So, both these interesting effects in relativity are brought out from the Lorentz transformation equation itself. Thus, we can clearly see that simultaneity and clock synchronization are two very interesting relativistic effects that are quite different from our perceived notions based on Newtonian ideas. Thank you.